Welcome everyone, and thank you for taking time out of your day to join us as we officially launch VCS Canada. VCS started in the USA in 2014 and have been growing ever since. For a while now, we have been providing support to contractors in Canada and have now officially expanded into Canada with the start of our Canadian entity. At VCS, we specialize in concrete preservation, providing solutions to clients facing corrosion and concrete durability concerns. My name is Claire Spriggs. I'm an engineer at VCS, and I am from Winnipeg, Manitoba. I started working with VCS as a summer intern in 2019 and have been working with them ever since. Today, we will be hearing from four of VCS's very own, Pratik Murkut, Cheyenne Yazdani, Natalia Shanahan, and Brian Pales, each presenting on a case study. After each presentation, we will take one or two questions that have been posted into the chat and then move on to the next speaker. For any questions that we don't get to, we will hold them until the end and try and answer as many as possible. Again, we'd love to answer as many questions as possible, so to incentivize this, we will be handing out an Amazon gift card to the individual who asks the best questions, so please ask away. And without further ado, let me introduce you to our first speaker. I will try and keep these brief and just hit the highlights. However, please note this definitely doesn't do justice to their very extensive resumes. First off is Pratik Murkut. He is an engineer at VCS and has been working with us for 2 years now. Pratik has his doctorate degree in material science from Oregon State University and is a NACE certified technician. Pratik is a bit of a shutterbug, so when he's not busy at work, he is busy with his photography. Today, he will be talking to us about a case study utilizing two-stage cathodic protection, and I will let Pratik take it from here.
Thank you, Claire, for that introduction, and thank you everyone for joining us this afternoon. So VCS often works on marine infrastructures like docks and with different port authorities. And today I'm going to talk about one of the rehabilitation projects we did with the Port of Corpus Christi in Texas. VCS worked on extending the service lives of Oil Dock 4 and 7, and this project actually won the Award of Excellence at International Concrete Repair Institute in 2021. This project will essentially highlight the value engineering VCS brings to the table. So the lower level substructure elements of these docks, specifically Oil Dock 4 and 7 at Port of Corpus Christi, were showing signs of deterioration due to corrosion. And since these elements are at waterline, they are constantly exposed to tides and tidal spray. So thus, the steel reinforcement over time undergoes corrosion, which effectively leads to degradation of reinforced concrete beams and column piles. And owing to this deterioration, the owner wanted these elements repaired and rehabilitated via cathodic protection. But before we dive into cathodic protection systems, I'll quickly go over the basics of corrosion of steel and concrete. So essentially, what I'm trying to say is, so when we talk about corrosion, most people think about red or brown rust, but that's only one part of the corrosion reaction. And here are the schematics showing the corrosion reaction occurring. And we have an anode forming on the rebar, and then we have a cathode forming on the rebar. So anode is where the section loss or loss of metal or rust formation occur, whatever you like to call it. And so wherever we have an anode, we need to have a balancing cathode to complete the electrical circuit. Essentially, the key takeaway from this slide is that anode is where the section loss occurs and cathode is where there is no section loss. So essentially, there are numerous ways to mitigate or slow down the corrosion process of the rebar, and one of the means is by cathodic protection. So in cathodic protection, the intention is to make the corroding structure a cathode so that we will not have any section loss whatsoever. And if we have a structure that's at a risk of corrosion, and if we make all of our structure a cathode, and we make something else the anode, then we'll have protected our structure from the section loss. And there are two main types of cathodic protection system. One on the left shown here is the galvanic cathodic protection system, and on the right is the impressed current cathodic protection system. So in the galvanic cathodic protection system, we take a galvanic anode and we directly connect that anode to the steel we are trying to protect. And now galvanic anode will sacrificially corrode to protect the steel, thus making a steel a cathode in the process. And typically for these systems, we use zinc, aluminum, or magnesium galvanic anodes because these three metals are less noble than steel, so they are going to sacrificially corrode to protect steel. And so in ICCP system, we use any power source, let's say AC power, like a regular outlet, solar power, wind power, or anything that generates energy. And we deliver that energy in the form of electrons to the steel in the form of DC current. And that's where the rectifiers come into picture. In ICCP systems, we still use anodes as a delivery system, but then these anodes are now dimensionally stable, unlike galvanic anodes, which were sacrificially corroding. So for ICCP systems, we typically use titanium mesh with mixed metal oxides deposited on them, or we use high silicon cast iron anodes, which are stable as compared to galvanic anodes. So at Port of Corpus Christi, the substructure element had arc sprayed zinc system as their original cathode protection system. And since the original CP system was past its design life, the CP system could not adequately protect the elements from corrosion, so the port owner wanted to replace the old arc spray zinc system with the new one. So to give you a little background on how the arc spray system works, so essentially in this technique, you spray layers of zinc metal on the concrete surface and then connect it to the reinforcing steel so that the zinc layer corrodes sacrificially to protect the steel. Now, this technique uses a sprayer unit, which is shown on the bottom left, which has like two reels of high purity zinc wires, which are essentially, let's say, like 99.9 purity zinc. So pure zinc comes off of these wheels, go through the arc welder, and then arc melted and sprayed onto the concrete surface. Now, in order to form a strong bond between zinc layer and the concrete surface, a lot of surface preparation is required, which involves sandblasting, cleaning the concrete surface beforehand, and then spraying the zinc metal on the concrete surface. Ideally, you would want to have the surface preparation done on the very same day as you would like to get the spraying done on. And the schematic on the bottom right is where you have a couple of zinc layers sprayed on the concrete surface, and then the system is connected to the reinforcing steel through a rod and a plate, so that so this provides the electrical connection between the anode, which is the zinc, and the steel, which we are trying to protect. One of the interesting things about this job was the initial bid scheduling constraint. And because it is a active oil dock, and obviously we don't want to interrupt the loading and the unloading cycle of the oil. So port had a very strict schedule of the number of days we were allowed to perform the hot work. And the way they define hot work is that any work that involves burning, welding, using fire, or any spark producing tools, or anything that can produce a source of ignition, that is how it's categorized as hot work. So here in the RFP, as an example, you had only like 3 days, 3 one-day windows, 4 two-day windows, and you had 1 3-day window. So effectively, you only had 14 total days in a month to get the work done. And for the arc spray system, this posed a challenge because zinc metallizing is almost all hot work, and thus we cannot do hot work when the ship is docked at the berth, as it requires sand blasting on the concrete surface, making electrical connections to the rebar that require drilling holes. And so that's a hot work involved there as well. And there's a lot of surface preparation and then spraying. And in addition, the prep work can be lost because of an outage. So let's say, for an example, if you have only a 1-day window to work and you have to get all the prep work done, and after that you have to do the spraying of the zinc or zinc metallizing to do on the very same day. And if you don't get it done, then you have to come back and redo some of that prep work. So there is a lot of risk of having to redo the work. And furthermore, since metallizing generates a lot of zinc dust, environmental control for like personal safety added to the cost. So the initial bids came in really expensive or really high. So to fix this problem, VCS worked with JM Davidson, who was the general contractor for this project, to figure out an alternative CP solution to reduce the cost and effectively utilize the shutdown days without disrupting the operation at the oil terminal, where you cannot work when the ship is docked at the berth. So VCS reviewed the project requirements, identify the driving forces for hybrids, and essentially answered one important question, which was, how can we better utilize the days where hot work was not allowed? So we looked into the cathodic protection system that allowed us to be more efficient with the shutdown days. So the option of drilled-in galvanic anodes was explored. Although galvanic anodes option would still require some amount of hot work, like drilling holes, cutting chases for anode wiring, but the shutdown days could be more efficiently or effectively used by performing, let's say, anode wiring or grouting, which essentially have no hot work involved when the ship is docked at the berth. So effectively, the hot work for galvanic anode option was limited to drilling holes and cutting chases for the anode or the anode wires, as opposed to extensive hot work which was required for metallizing. So for the drilled-in anode option, innovative product called fusion anodes was used, which is essentially a two-stage anode combining both galvanic and impressed current phases into a single drilled-in anode, wherein you have a piece of zinc that acts as a galvanic anode, but you also have a AA alkaline battery that provides an initial impressed current discharge, which creates the passivation on the structure. And then the zinc metal core takes over to maintain that passivation for the remaining service life of the anode. So these two-stage anodes can effectively protect the structure anywhere between 20 to 25 years, depending on the exposure conditions and several other factors. So typically, a drilled-in anode option would be slightly more expensive than metallizing, but because of the hot work limitation on this project, this was actually a cheaper option because you don't have to redo the work. For example, when you have hot work opening, you can just drill the anodes into the concrete, and then when the ship is docked at the berth, you can just grout and wire the anode. And even if you have to stop the work, the next time you come back, the anode holes are there, ready for the anodes to be placed in. So essentially, there is no loss of prep work, so to speak. These are some pictures showing contractor drilling anode holes or grouting anodes, and when they were on the elevated beams under the slabs and on the waterfront beams as well. So when the ship was docked at the berth, no drilling or cutting was performed, and only anode wiring or grouting was performed, thus avoiding the hot work completely and efficiently using the downtime. And in normal circumstances, metallizing would have been cheaper, as I've already said. But had it been a regular dock where you could perform metallizing, like anywhere, anytime or whenever, it would have been a cheaper option. But since it was an active oil terminal with hot work limitations, galvanic anode option was a more effective solution in this case. And here is a photo of some drilled in holes, and then again, those anode holes grouted in, and that's what it looks like as a finished product or after everything is done. And here is what it kind of looked like when it was completed. There's some repair work. And so this is where the anodes were installed on the top of the beams. And so the owner wanted to monitor the performance of the CP system in various areas of the structure. And here is what a monitoring junction box looks like, where a CP technician or an owner's representative can come with just a multimeter and monitor the performance of the system over time. And here is what the close-up of a monitoring panel looks like, where you have an anode connection, a structure connection, a shunt to measure the current running between those two, and then you have an on and off switch to do some diagnostics testing that allowed the owner to go and measure the performance of the galvanic CP system over time. And I'm happy to report that this system is functioning optimally, and we are working. A similar kind of system is being installed on Oil Dock 8 and 9, and VCS is providing QA/QC for the same job. Thank you so much, and I'll be happy to answer any questions you guys might have.
Yeah, I have a question here. How does the service life between galvanic anodes and metallizing compare?
That's an excellent question. There are several factors which contribute to the service life of any system, may it be galvanized, metallizing, or fusion anodes. But typically, well, the factors can be like how much steel are we protecting, or what is the exposure condition? Does it have too much chloride exposure? Things like that. But typically speaking, metallizing can last anywhere from 10 to 15 years. But again, it is dependent on the conditions. whereas the fusion anodes can last anywhere between 20 to 25 years. And if you compare these two systems, if you talk about ICCP systems, when you have like dimensionally stable anodes, the anodes can last for a long time. But again, the bottleneck for ICCP service life is dependent on the quality of electronics you use or like how frequently it is being maintained. So these are the factors which come into play.
Thank you. We're going to move on to Cheyenne now. So our next speaker is Cheyenne Yazdani, who is one of our project managers at VCS. He started at VCS as a summer intern and has now been with VCS for 6 years. Cheyenne has his master's degree in civil engineering with a focus on materials from the University of South Florida and is a NACE certified technician. When Cheyenne isn't busy at work, he does enjoy spending his time playing volleyball. Cheyenne will be sharing with us a case study on corrosion assessment and design of surface applied cathodic protection. So Cheyenne, the floor is yours.
Thank you very much, Claire. I'll go ahead and share my screen here with everybody. So VCS conducts a lot of corrosion assessments and evaluation on a variety of structures as well. And today I've selected the triple-decker bridge located in Chesapeake, Virginia, with everybody to discuss. The bridge was originally constructed in 1948, so as of this year, it's about 74 years old. And it consisted of 3 levels. Level 1 was an on-grade road. Level 2 and 3 provided vehicular traffic. And level 2 provided train traffic as well. This was a cast-in-place construction, with the exception of level 2, which had steel girders to support the cast-in-place deck. And the owner of the bridge was the city of Chesapeake. And so they requested VCS to conduct a corrosion and material assessment of the bridge elements, including the abutments, piers, decks, and beams, and to provide a rehabilitation strategy option for them to be able to extend the service life of the bridge once the study phase was over, and based on the selected strategy to provide a cathodic protection design and on-site QA/QC services during the construction phase. And so, VCS conducted ground penetrating radar, which is an electromagnetic evaluation method for concrete. This method helps us identify the reinforcement layout and also the cover depth of the steel in the concrete elements, which is vital for proper assessment. And it also can be used for qualitative condition assessment of reinforcement. And so based on the scans that are obtained, an example of that is shown on the right there, we can identify qualitatively if there are any chloride or moisture or concrete deteriorations based on the attenuations that we receive from the GPR signal during the testing phase. And so this is the top image and scale, or an image of the cover depth analysis that was done. And we could map this out to visually identify clearly where the areas of low cover are, which are important in structures corrosion and assessment. And so the areas that are highlighted in light yellow and dark yellow are areas where there are low cover depths between 1 inch to 1.5 inch. And the image on the bottom represents the amplitude analysis that's conducted that provides us that qualitative analysis of the elements. And so any areas that we receive poor signal are indicated in the dark red to light yellowish areas. And those are areas that we tend to look at closer and identify what the root cause could be with other assessment tools. And so one of those tools is the corrosion potential measurement, also known as half cell potential. And this is conducted based on ASTM C876. And it provides us an understanding of the probability of active corrosion that's present in the element that we're studying. And so first, in order to conduct this test, we have to establish a connection to the reinforcement inside that element and connect that to our voltmeter or multimeter's positive terminal. And we also use a portable reference electrode. Typically with concrete structures, it's a copper sulfate reference electrode, and we connect that to our negative port in our multimeter. And based on specific grid patterns, we collect data, and it tells us the potential difference of that steel that's embedded in the concrete versus the portable reference electrode. And if the potential difference is very high, then those areas are then mapped out. And again, that's another tool that we can identify areas of high active corrosion probabilities. And so the image on the bottom left shows us a map that was put together after the test was completed. And the figure on the bottom right shows us a scale of what we use to interpret the data. And so any areas that are typically, more electronegative than negative 350 millivolts, those are areas that there's a high probability of active corrosion that's present. And so in the bridge deck, we can see areas that are yellow or orange and some are red. And so those are areas that we would look at closely to see what is happening in those locations. We also used impact echo sonic ultrasonic velocity testing, and this device uses a set of 4 sensors that can be seen on the image on the left-hand side, and also an impact device. And so what happens is the impact device is used to impact the concrete surface, and compressional and shear waves are sent through the concrete, and based on the thickness, that wave travels into the concrete, reaches the bottom cover of it, and bounces back up to the sensors, and it's picked up by the sensors. And based on the time it takes for the waves to travel, we are able to identify if we're dealing with sound concrete or if there's some sort of delaminations or micro crackings present inside that concrete element. And so in this image on the right-hand side, this device also helps us identify in situ compressive strength, so we can see visually map it out and see where areas of low strengths are. And so it's very helpful in identifying compressive strengths as well. We also conducted material sampling in the form of concrete powder samples and concrete cores from various locations of the bridge deck to determine the chloride concentration levels. And this test, chloride concentrations are typically looked at with relative to the depth of the concrete. And so in the graph on the top right corner, we can see the various, on the x-axis we have the concentration levels, and on the on the y-axis we have the concentration levels, and the x-axis are the concrete depths. And so we are able to see how much chloride level is present at various depths of the concrete, which can significantly affect the corrosion rate and corrosion activity of any reinforced concrete structure. And so in the areas that we collected concrete cores, we used an indicator to spray the core and identify if the pH level of the concrete is relatively high, which indicates to us there's a low probability of corrosion activity, or if the pH is low, that could cause corrosion activity. And this is carried out by carbonation. Typically, when concrete carbonates, we can see the change in pH level. And so we can see in this core example, the first quarter of an inch is probably carbonated, but it's not a concern really, because the rest of the core has a very high pH level and it's above 9.5. And so once the study was completed on site, we found out that there is active corrosion present throughout the majority of the structure and substructure elements of this bridge, and this is largely due to chloride ion penetration into the concrete due to de-icing salts. And carbonation was present in some locations, but it wasn't a leading factor in the corrosion activity that we saw. And so we provided 3 rehabilitation options to the client. Option 1 being basic repairs and immediate needs, where deterioration was to a point where there was spalling present, and we recommended to remove all the areas of concern and install galvanic type 1A anodes around the patch perimeters to eliminate the halo effect and further deterioration happening. Option 2 was to address areas of concern where we see there is some corrosion activity, but it's not enough to cause physical damage as of today, but it could cause delamination and spalling if left untreated in the long term, and also conduct all option 1 recommendations. And lastly, we proposed a global corrosion protection or cathodic protection in the form of arc spray zinc, which Pratik covered with us. Ultimately, the client decided to select option 3, which was to apply a global cathodic protection system in the form of arc spray zinc in all the deck and underside beams, abutments, and piers, and also address the patch areas and areas that are spalling. And so in the image on the bottom left, we can see all the hatched red areas are where arc spray zinc would be applied to protect the structure. And the image on the right is in the hatched areas are where the patch repair locations are, where type 1A galvanic anodes would be installed. And with that, I'm open to any questions if anybody has any.
Yeah, I have a question here. How do you determine the type of tests that you're going to perform when you do an assessment?
That's a great question. You know, with corrosion evaluation, we tend to conduct multiple tests, and we like to layer them together and look at different things and add different components to our study. So, you know, cover depth is very important in a corrosion study. Half-cell corrosion potentials are vital. So based on the structure itself and the client's needs, we tend to select the most appropriate methods and make sure that the tests that are selected can help us in identify the root cause of the problems.
Thank you. We're going to move on to our next presenter, who is Natalia Shanahan, a Senior Project Manager with VCS. Natalia has been with VCS for 4 years and has 12 years of experience in the civil engineering industry. She has her doctorate degree in civil engineering materials from the University of South Florida and is a NACE certified technician. Natalia does have a bit of a green thumb, so outside of work, she enjoys spending time in her garden. And today she'll be talking to us about post-tensioning in reinforced concrete parking garages, and I will let Natalia take it away now.
Thank you, Claire. In addition to port structures and bridges, VCS does a lot of evaluation of parking garages. Most parking structures use unbonded post-tensioning reinforcements, but we've also done a few projects on structures that have bonded PT. Unlike corrosion of black steel rebar, corrosion of high-strength tendons is very difficult to identify visually. With rebar, appearance of delaminations and spalling typically corresponds to approximately 10% rebar section loss. But with high-strength tendons, due to their small cross-section, cracking may not occur until there is complete section loss, which can have a significant effect on the structural capacity of the element. Compared to rebar and grouted PT, unbonded PT strands don't have the same level of protection because they are not encased in a cementitious grout or concrete, and because of that, they can't form a passivating film on the surface of the steel. Typical defects that increase the risk of corrosion for the unbonded PT are breaks in the sheathing. They allow moisture and chlorides to access the strands, poor greasing, and improperly kept anchors, which can potentially expose the tendons to the outside environment. Sacred Heart Hospital parking garage was an example of an unbonded PT parking garage. This garage had a number of broken tendons, which were visible from the outside. They were just sticking out of the edge of the slabs. Inside the garage, there was an issue with cover depths on the top of the slabs. This is an example, this is an extreme example where this particular tendon had virtually no cover depth and was exposed to traffic and the external environment. On the underside, there were a number of spalls that also exposed the PT. There were also issues at the anchorage. Some of the tendons were completely missing their grout caps, as you can see here, but majority of the tendons had cracking around the perimeter of the grout caps and were leaking grease. While we were on site, we were fortunate enough to have a rain event, and could see water leaking through the joints on all levels of the garage. But even before the rain, there were signs of leaking throughout the structure, which you can see here. So how can we evaluate the corrosion risk for unbonded PT tendons? This can be done using the post-tech corrosion evaluation method. In this test, 2 small holes are drilled to the depth of the tendon, and then we use a screwdriver to open up the sheathing. Then we install 2 ports, an in port and an out port. We connect a cylinder of dry gas to the in port. You can see an example here. The cylinder forces dry gas into the tendon, and this causes the air inside the tendon to flow through the out port. At the out port, the air passes through the dew point meter. This is an example of the dew point meter connected to the out port. And the dew point meter measures the temperature and the relative humidity of the air inside the tendon. Then these values are plotted onto a chart that classifies the tendons either as dry, no risk for corrosion, wet dry, moderate risk for corrosion, or wet, where the risk for corrosion is high. Example of that here. In this case, we don't test the tendon. We mark it as wet, 100% relative humidity, because there is bulk water inside the sheathing. Another type of defect we sometimes see during the testing is moisture coming out of the anchorage. This can be seen in the bottom photo here. This is the out port, and when we pushed dry gas through the tendon, we saw water seeping out through the anchorage, and air was escaping from the anchorage as well. Ellis Hospital parking garage in Schenectady, New York is another example of a garage that uses unbonded PT. Here we also did the post-tech corrosion evaluation of the tendons, but in addition, we did openings to visually inspect the condition of the tendons and do the screwdriver penetration test. The screwdriver test is done to assess the tension of the tendon. If the screwdriver can fit between the individual wires and move them, this indicates a break in the tendon. The example of that you can see here in the bottom tendon. The screwdriver was easily able to move the individual wires. So this indicates that the tendon is broken. The tendons that are still under tension, the screwdriver would not be able to fit in between the wires. So these were the beam tendons, and although they were visually in good condition and there was grease inside the sheathing, the bottom tendon was broken. The tendons on the left are an example of the slab tendons. Slab tendons were generally in worse condition compared to the beam tendons. In the top tendon, there's severe corrosion, but it was still possible to identify the individual wires. The bottom tendon was very corroded to the point that it was not possible to identify the individual wires, and it was just one single mass of corrosion product that had completely filled the sheathing. Before we did the opening, we did the post-tech corrosion evaluation on the bottom tendon, and we were not able to pass dry gas from the in port to the out port. And once we did the opening, we saw that it's because the sheathing was completely filled with corrosion products. The Milwaukee Airport parking garage is an example of a parking structure that uses bonded PT. This garage had bonded PT in the beams. With bonded PT, the typical causes of corrosion are the presence of voids and soft grout inside the tendon ducts. These defects can be identified with impact echo testing using the same setup as Cheyenne described earlier. So here you see the impact device and the force sensor array. The principle behind this testing is that the wave generated by the impact will travel through a fully grouted duct, be reflected from the back surface of the element, then travel back and will be picked up by the sensor array. This will result in the measured thickness of the element that is the same as the true element thickness. But if there are voids or soft grout in the duct, the wave will need to travel around the void, which will result in a greater element thickness. For this testing, the tendon profile is first located with GPR, as you can see here, and marked out in 1 foot increments for testing. After the location of the defects is determined by impact echo, these locations are drilled for borescope inspection. This is a minimally destructive test that requires only a small hole. This allows us to visualize the extent of the void and condition of the strands. Another type of testing that VCS can perform on unbonded PT is lateral deflection testing. The example of this testing was the Grady Cass parking garage that was under construction, and the structural engineer was concerned about the tension in the tendons. For lateral deflection testing, a 2 foot long opening is chipped out around the tendon. And then a testing frame, which you can see in this image, is attached to the tendon. Then a known force is applied perpendicular to the tendon, and the deflection of the tendon is measured. The value of the force and the corresponding deflection then allows us to estimate the tension in the tendon. Thank you for your attention, and I would like to take questions if there are any.
Yeah, I've got a question here for you, Natalia. What are the rehab methods for PT?
With unbonded PT, tendons that are still in good condition structurally can be dried out by passing dry gas from one end of the tendon to the other and then re-greased. With bonded PT, voids can be regrouted.
I have another question here. How many tendons do you typically test?
We typically try to test approximately 10% of the tendons, but that really depends on the budget. But normally we try to test 10%.
Thank you. We're going to now move on to our final presenter, Brian Pales, our principal engineer at VCS. He has been with VCS since the beginning, so 8 years now, and has over 13 years of experience in the industry. Brian has his doctorate degree in civil engineering with a focus in structures from Rutgers University. He is a NACE certified corrosion specialist and is vice chairman of the NACE Standards Committee for Concrete Infrastructure. He is also very into landscaping, so when he's not busy at work, he is busy in his yard and actually built his very own putting green in his backyard. Today, he will be presenting on non-destructive evaluation and corrosion assessment of various structure elements, and I will let Brian take it from here.
Thank you very much. Today, I'll be talking about the evaluation and repair of cement silos, reinforced concrete cement silos. So these silos are at a cement manufacturing facility and hold clinker that comes off the kiln. So it's a quite hot material. And so these silos are subjected to various loads and also heat stress. And as you can see here, they're built in silo clusters. So in this cluster here, there happens to be actually 9 silos that are together. And we were asked to come take a look at these silos because of issues with cracking and deterioration of various elements. These silos are constructed using slip form construction. So it's a rather rapid technique to build silo structures where they move the forms rapidly vertically, and as they're moving vertically, they're casting the structure on top of itself. So with that, we'll be talking about an assessment and rehabilitation. So the first thing we were asked to look at on this structure is the ring beam columns. So in the silos, at about a third of the way up on the vertical elevation, there's a hopper at which the material inside the silo can be unloaded. And that hopper is supported by a ring beam, which is around the circumference of the inner silo, and then it's supported by 4 columns on each silo. And so here's a schematic of 2 adjacent silos and kind of how the ring beam and the columns are aligned. So we'll be looking at silos 8 and 9. And the issue that was with the ring beam or with the columns is they had concrete deterioration on the columns. That deterioration was observed in the form of some vertical cracking and delamination. In the photo on the left there, you can see the vertical cracking, and then it's a little harder to see, but there are red chalk lines indicating that that concrete is all debonded and unsound, as we had conducted hammer sounding in these areas. And so, and then also there were areas of concrete that spalled off. So the photo on the right there is an image of concrete that has actually come off the structure and has exposed the reinforcing steel. You can see that there is the spiral reinforcement and it's heavily corroded. And you can also see that there is quite a sufficient amount of cover depth over this reinforcement cage. It was actually close to 3 inches of concrete cover, which is quite a lot in most types of these kinds of structures. So we were asked to kind of understand the extent of this deterioration and what was the cause of this deterioration so that it could be repaired. The first thing we looked at was carbonation. So is carbon dioxide lowering the pH of the concrete? So we broke some fresh sections of the concrete and then sprayed the pH indicator solution on. And you can see the pink area is where the pH is high, and then the clear area at the top is where the pH is low. So it's about maybe 3/4 of an inch into the concrete, the pH is lowered through to carbonation, but the remaining thickness of the concrete cover has a high pH. So with a cover depth of around 3 inches, carbonation really is not an issue for this structure. The next thing we looked at was chloride concentration of the concrete. So if carbonation isn't the issue, then most likely it's chlorides. And so we took concrete samples and tested them in the laboratory for chloride concentration. And you can see here we did different depths from the surface to the depth of the steel, which is about it looks like 3.5 inches deep. And so we were measuring the concrete concentration at different heights as well on different columns. And you can see that the top 2 entries have pretty high chloride concentrations. The chloride concentration at the steel depth that caused corrosion is around 350 parts per million. So at that concentration, the chlorides break down the passive film and allow for the steel to initiate corrosion. And you can see the first 2 entries, they have chloride concentrations that are above that 350 threshold at 700 and 500 and so on. So at these chloride concentrations, corrosion is definitely active due to the chloride exposure. You'll notice that those 2 samples are collected from an elevation at 3 and 5 feet respectively from the ground elevation. And so they're pretty low on the columns. But then the samples we collected at 30 and 24 feet from the ground have very low chloride concentrations, almost negligible. And so we can see there's really an association with the elevation and the chloride concentration. And due to the location of where these silos are, they're quite close to, one thing is they have, the ground has salts in it. So they're close to the ocean. So the soil is sandy and it has salts in it. And so what is happening here is that the groundwater is got high concentrations of, or some concentration of salt, and it's wicking into the columns, and then the water is evaporating when it wicks into the columns and leaving behind salt. And so what's happening is over time there's salt buildup in the lower elevation of these columns. That salt buildup is then getting to a concentration that will initiate corrosion. So over time, the water is just wicking through these columns at the lower elevation and just depositing salts. So the next method we wanted to see was, where is active corrosion on the columns? So now that we know that chloride is in sufficient quantities in there, we wanted to see where corrosion is active. So doing the corrosion potential survey that Cheyenne discussed earlier, we measured the risk for corrosion activity on several of the columns, on surveying 4 faces all the way up to the top of them. And you can see that from about 10 feet up, the potential measurements were very passive. They were well above positive 50 versus a copper sulfate reference electrode. So that's an indication that corrosion is not, the risk for corrosion is very low. However, the lower 10 feet had a much lower corrosion potential. Now, the values were not below negative 350, which would be typically the value that most people would expect associated with corrosion activity and corrosion potentials based on ASTM. And you see the scale down there. ASTM has an appendix that says that, more negative than negative 350 indicates a high probability of active corrosion. However, that's in certain environmental conditions and under certain instances. Even though the values aren't that low, there's still a big potential difference between the upper 10 feet and the lower 10 feet. And as we know, with the potential difference, you drive current flow, and so that allows for corrosion. And so while the potentials aren't very low, they are quite different from the passive range. And so that's an indication that the lower 10 feet are actively corroding. And so we can see it's pretty consistent across the columns, is that the lower 10 feet is actively corroding, and that's where we're seeing the chlorides deposit, which makes sense. The next thing we wanted to do was survey the condition of the silo structure itself, so the walls and the ceiling. And for that, we used impact echo. And so you can see the photo on the right, that's us in the interior of the structure actually doing the impact echo testing. So we've got the array sensor there and the impactor. They emptied the silos and erected scaffold on the inside. This can also be done from the exterior. But for certain reasons on these silos, we had to do it from the inside because of the clustering. We couldn't get access to the full exterior and also debris on the outside of the structures. So as Cheyenne had mentioned, impact echo, one thing we're looking at is we're impacting and looking at the wave bouncing between the section to identify for delaminations and other damage like that. And then we're also looking at the wave velocity horizontally between the sensor array to identify the in-situ concrete compressive strength to see if there's any cracking or deterioration of the concrete. So the first thing we looked at was the roof slab. So there was a concern of deterioration on the roof slab because a few spalls had started to form. And on the image in the screen here, you can see that there are a few hatch marks where there's spalled concrete that has fallen off. So what we did was we went through and used impact echo on a grid to survey the structure and identify if there's any deteriorated concrete beyond the spalls that have already fallen off. The yellow area are areas where there is minor delamination, and the red areas where there's serious delaminations as identified by the impact echo. Serious delaminations would be delaminations that are near to a spall, so they might fall off soon, where if you hit them with a hammer, you would hear them kind of on the hammer sounding, you hear that echo. The minor delaminations would be if you hit those with a hammer, you wouldn't hear any difference, but the more sensitive equipment of the impact echo pulse velocity device is picking up micro cracking that's occurring there. So those areas are going to be large delaminations in the near future. And so those are areas that we would recommend be repaired now because they are going to become larger in the near future. And so with the impact echo device, not only can we identify similar results to a hammer sound, but we can also find areas that in the future will become those large delaminations. So we can be much more proactive in our repairs. Another thing we looked at was under where the roofs rest on the column on the silo walls, they use beams and have beam pockets that rest on that thin silo wall. So we were asked to look at the concrete quality in the loading zone of that support. And so effectively we did a impact echo pulse velocity testing directly under those beam supports and looked at the concrete quality, specifically what's the apparent concrete compressive strength. And you can see here's one example where in that loading zone, you can see that the concrete compressive strength in some areas falls well below 3,000 PSI, which would be considered very low for concrete compressive strength. Typically, we would want concrete compressive strengths over 4,000, but a structure of this age, it may have been 3,000 when it was originally constructed. So things that are in the orange and red are well below the kind of compressive strengths we would like from a structural standpoint. So by going around the silo walls, we can identify where areas of these concrete deterioration is and this apparent weakness so that they can identify areas that are in trouble and need a repair. For the columns, because of the corrosion nature of the deterioration, we designed a galvanic cathodic protection system. So what we designed was the bottom 10 feet of all the columns would be removed, the cover concrete, the steel would be cleaned, 7 galvanic anodes would be, or 8 I believe, would be installed around the perimeter of the column. Those galvanic anodes would mitigate further corrosion of the steel, and then the concrete would be cast back. And so here you can see the design schematics for that repair. In addition, there were some isolated small singular patch repairs on some of the columns due to some abrasion and some other damage. And so for those, we installed designed to install some single discrete anodes that would be installed in those patch repairs that are small. So on the columns, first they removed the cover concrete, and you can see here's one example of that. And you can see on the right where the steel is corroded through in some instances. Then the steel is sandblasted clean to remove all the corrosion product. And then the galvanic anodes are tied onto the column. And here you see on the left where the large repair that you have the long DAS type anodes. So those are very efficient in large areas. And then in the small little patch repair areas, discrete anodes are placed in those areas. And in the columns, they then form that back up. You've got like a sonotube there, and then they form that back up and cast it back. And due to the kind of the proper cover over the galvanic anodes, they added a little bit of cover to the original concrete structure. But you can see this is the finished column. And so now that bottom 10 feet is galvanically repaired. So any chlorides that are getting in there their effect is mitigated by those galvanic anodes. So with that, thank you. I'll happily take any questions.
Yeah, I have a question here for you. How does the 350 ppm is compared to the 0.025% mass of concrete listed in the code?
So really, that's just different units that we're using. So, you know, there are different units that you can use to evaluate chlorides, but they all mean the same. So whether it's percent by mass of concrete, percent by mass of cement, or parts per million, they're all kind of getting you to the same number. It's just different. It's just a different units to use. For instance, like meters and feet.
Okay. Another one here. Are there cathodic protection systems that could potentially be used in a precast concrete parking structure that would be limited to the reinforced concrete topping?
Okay, so to the reinforced concrete topping. So if you have a reinforced concrete topping and you need to do galvanic or cathodic protection on the topping slab, you can do embedded anodes from the top. Galvanic anodes can be drilled in and grouted in on the grid on the top. Or, you know, if it's just for repair areas, when you remove that concrete, you can tie them into that repair area. You could also do a press current overlay or impressed current drilled in kind of rod style anodes as well. So there's a lot of different options. An overlay you would treat just kind of like a normal slab. You could do the same kind of galvanic or impressed current cathodic protection as you would there.
All right, thank you. Next question is, could you clarify the benefit of knowing the cause of corrosion? Does the repair approach change if whether it's carbonation or chlorides?
So knowing the cause is important, especially with regards to designing a corrosion mitigation system, because the amount of current that you need to protect the steel changes depending on the cause. So for instance, carbonation tends to be a slower type of corrosion, and it tends to be a little bit more global on a structure. It's happening most places. And so you would need more of a global application for corrosion mitigation, but you wouldn't need as much protective current to mitigate that. Whereas chloride corrosion can be very localized sometimes, but chloride corrosion is much more accelerated. So you need more corrosion protective current to stop that. So definitely knowing the cause will help you better design the solution.
Okay, I'm going to go back up to some of the questions we had to hold. Does the cathodic protection cause any embrittlement in the reinforcing steel with time?
So hydrogen embrittlement is really only a concern when we're talking about post-tension or pre-stressed strands. So those strands, hydrogen can get into that and cause embrittlement. It's not a concern for conventional rebar. Hydrogen evolution can really only occur with impressed current cathodic protections systems. Galvanic or even hybrid systems that are mostly out there do not have the potential enough to. What effectively happens is water breaks down into oxygen and hydrogen if you have a driving potential that's too high. So galvanics can't drive the potential high enough to cause that. Only impressed current systems can. So on conventional reinforced structures, there's never a concern with it. With post-tension or pre-stress structures, we can use galvanics, and there's no concern of that problem. We do not typically recommend using impressed current systems on those types of structures because you can cause hydrogen embrittlement, but that's only with impressed current systems. And so galvanics are completely fine with those.
I'm just going to try and squeeze in one more question. How well does the compressive strength from the pulse velocity testing compare to compressive strength from cores?
So it all depends on the crack amount or an orientation. So if you have a core and there's a crack perpendicular to the loading plane, that crack really won't affect the overall compressive strength of the concrete, but it will affect the impact echo pulse velocity method. So no, crack orientation can have an effect on the pulse velocity impact echo, while sometimes has a limited effect on the core, or sometimes has a large effect. So it's really about core cracking. But in general, they are pretty closely related, and will be off just based on the cracking and the quantity and direction.
All right. Thank you, Brian, and thank you to all four of you guys for presenting today. I want to thank all of you guys for participating today and for your great questions. And just a quick note to finish this off, we are a friendly and experienced group of professionals, and we really look forward to supporting you with any and all corrosion assessment, non-destructive testing, or cathodic protection design related challenges. So please do not hesitate to reach out at any time. You have our contact information posted up here. We are planning trips in the near future to various communities across Canada and would love to meet you in person. Our first trip will be Natalia traveling to Vancouver in May. Just a quick note, if we didn't get to your questions, please reach out to us via the information on the screen. And again, thank you for joining us today. We are extremely grateful you decided to spend your valuable time with us.
Thank you very much.